Okay, welcome back. Today, we're diving deep into Earth's magnetic field, our planet's invisible, vital shield. We've got some fascinating new data detailing some really massive shifts happening up there.
It really is our first line of defense against nasty stuff, from space, cosmic rays, solar radiation, you name it. But yeah, the focus today is this. Oh, this growing dent in the shield, a big one.
A dent, right?
Yeah.
The South Atlantic Anomaly, or SAA, it's not exactly new news. People have known about it for a while, but the latest satellite info, especially from ESA Swarm mission, it paints a picture of, like, rapid change.
Shocking change, almost. I mean, think about this. Since just 2014, this weak spot has grown by an area almost half the size of continental Europe. It's ballooning.
Half of Europe, that's huge.
It is. And it's not just getting bigger, it's changing shape. And that's already causing real headaches for satellites flying through it. So, yeah, let's unpack this.
Okay, let's start with the basics. You said it's been known since the 19th century. So where is this thing, this SAA?
Well, the name gives it away partly. It's primarily located off the coast of South America, but it really stretches out across the South Atlantic and increasingly towards Africa.
And you called it a dip in the field. What does that mean in practical terms, like altitude?
Yeah, this is where it gets pretty dramatic. So normally the magnetic field extends way out. Think typical low Earth orbit altitudes, around 400 miles, maybe 650 kilometers. Protection is good up there.
Okay, standard operating altitude for many satellites.
Right, but inside the SAA, the field dips way, way down. We're talking protection effectively dropping to maybe only 120 miles, that's about 200 kilometers, above the surface.
Wow, okay. That's a massive difference. Less shield, basically.
A lot less shield. And remember, this shield isn't generated on the surface. It originates deep, deep inside the Earth.
Right, miles below us. It's the core, isn't it?
Exactly. Deep down, about 1,900 miles, 3,000 kilometers beneath us, you've got the outer core. It's this massive ocean of incredibly hot, swirling, molten iron.
Like a giant planetary engine.
Precisely. It acts like a huge dynamo. The movement of that conductive iron generates electrical currents, and those currents create our global magnetic field.
So if the whole outer core is churning away, why this specific weak spot under the South Atlantic? You mentioned these reverse flux patches.
Yeah, that's what scientists think is the root cause.
Right.
Right near the boundary where the liquid outer core meets the more solid mantle above it, you get these strange areas, reverse flux patches.
And what makes them reverse?
Well, normally the magnetic field lines come out of the core, loop around the Earth, and go back in. But in these patches, the field lines seem to be doing the opposite. They loop back into the core locally instead of extending outwards.
Ah, so it's like a short circuit, kind of, weakening the field above it.
That's a decent way to think about it. It disrupts the outward flow, causing the field strength at the surface directly above that patch to drop significantly. Hence, the SAA.
Okay, that explains the why. Now let's get to the how fast. You mentioned the Swarm mission data, 11 years of continuous magnetic field measurements. What's the big takeaway from that recent data?
Speed and complexity. The expansion is dramatic, yes, but it's not just getting uniformly weaker or bigger anymore. It's evolving.
Evolving how? Not just a bigger blob.
No. The data shows the SAA has kind of split or maybe sprouted a second major weak area, a lobe extending towards Africa. So now there are almost two distinct centers where the field is weakest.
Okay, two low points instead of one. And is one changing faster?
Very much so. This new African center or lobe is where the magnetic field is weakening most rapidly. Chris Finlay, one of the lead authors on this, pointed out specifically that it's changing differently near Africa compared to South America.
Right, the weakening is more intense there. Do we have numbers on that? How fast is intense?
We do. That African reversal patch, the thing causing the weakening, it's decreasing in intensity really quickly. The rate is about minus 2.54 times 10 to the 5 nanoteslas per century. That's one of the fastest rates of change seen anywhere on the globe.
Okay, that sounds fast, even if the units are a bit abstract. And it's moving.
Yes. There's also a clear westward drift associated with this intense African weakening spot. It's not static, it's localized, it's accelerating, and it's moving.
And it's not just the weak spots acting up, right? The strong parts of the field are shifting too.
That's another key finding. While the South Atlantic is weakening, the traditionally strong magnetic regions in the northern hemisphere are also rearranging themselves.
Like what? What's happening up north?
Well, since 2014, the strong field area over Canada has actually weakened a bit. It's shrunk by an area almost the size of India.
Wow, okay. So Canada's weakening.
But interestingly, the strong region over Siberia has done the opposite. It's gotten stronger, growing by an area about the size of Greenland.
So let me get this straight. The SAA weak spot is growing and splitting. The strong Canadian spot is shrinking, and the strong Siberian spot is growing. All at the same time.
Pretty much, yeah. It paints a picture of a really dynamic, almost fluid system, not just a static shield.
And does this connect to the North Magnetic Pole's recent wandering?
Absolutely. These shifts in the strong northern regions are directly linked to that rapid movement of the North Magnetic Pole away from Canada and towards Siberia that we've seen in recent years. It forces updates to navigation models constantly.
Which brings us to consequences.
Yeah.
If this is all happening thousands of miles down and hundreds of miles up, why does it matter to, us down here or our technology?
Well, for us on the ground, it doesn't pose a direct threat. But for anything we put in low Earth orbit satellites, spacecraft, the space station, it's a major hazard.
Because the shield is weaker there.
Exactly. When a satellite flies through the SAA, it's exposed to much higher levels of charged particles from the sun and from deep space. More solar particles, more X-rays, more UV radiation.
And that radiation is bad news for electronics.
Very bad news. It significantly increases the risk of malfunctions, damage to sensitive hardware, communication blackouts. We see precautions taken all the time.
Like with the ISS?
Yeah, the International Space Station needs extra shielding specifically for its passages through the SAA. And the Hubble Space Telescope. It actually has to stop taking data when it flies through the region.
It just pauses science because of this anomaly.
Completely pauses, just shuts down data collection until it's out the other side. That tells you how significant the radiation environment is inside the SAA.
Yeah, it's incredible. Can you break down how the radiation actually harms the electronics? You mentioned 3 ways.
Sure. The first one designers worry about is called total ionizing dose, or TID.
TID, okay.
Think of TID like getting a sunburn, but for microchips. It's the cumulative damage from all that ionizing radiation passing through. Over time, it causes changes inside the silicon, like increased electrical leakage. It basically ages the electronics prematurely, changing how they work.
So slow degradation. What's the second type?
The second is displacement damage. This is also cumulative, but it's more like physical damage on a tiny scale. High energy particles literally knock atoms out of place in the crystal structure of materials.
Like tiny billiard balls hitting the silicon.
Kind of, yeah. A great example is solar panels. Flying through the SAA repeatedly can seriously degrade solar cells through displacement damage. We're talking maybe up to a 50% reduction in power output over a satellite's life.
Half the power gone. That's mission critical.
Okay, so those are cumulative. What about sudden catastrophic failures?
That's the third one. Single event effects, or C. And these are often the scariest.
Single event, meaning just one particle can cause chaos.
Exactly. A single high-energy proton or a heavy ion zipping through can hit a sensitive part of a circuit and cause an immediate problem.
What kind of problem?
It can be relatively minor, like a single event upset or SCU. That's just a bit flip, a stored 0 becomes a 1, or vice versa. Annoying might cause a temporary glitch.
Or it could be much worse. Things like latch-up, where the particle triggers a short circuit that draws huge amounts of current, potentially burning out the chip unless the power is cycled quickly. Or burnout, where it just instantly destroys a transistor. Catastrophic failure from one hit.
Yikes. And you can't really shield against these effectively, especially on smaller satellites.
Not easily, no. Shielding helps with TID and some displacement damage, but these high-energy single particles can punch right through typical shielding. So for C, it really comes down to careful component selection using radiation-hardened parts and clever circuit design to tolerate these events. It's a huge challenge, especially for, say, CubeSats built with off-the-shelf components.
Okay, so major danger for anything in orbit. But let's double-check for the folks listening. Absolutely no danger on the ground from the SAA itself, right?
Correct. Zero danger to life on Earth's surface. Our thick atmosphere does a fantastic job soaking up all those particles long before they reach us. We're perfectly safe down here from the SAA's effects.
Good to confirm. Though there is that one weird effect for humans who do go up there.
Yeah. Astronauts, particularly on the ISS, which passes through the SAA regularly, have reported seeing flashes of light, even with their eyes closed.
The shooting stars inside their eyes.
That's the phenomenon. It's thought to be caused by these high-energy particles directly hitting their optic nerve or retina, a direct reminder of the radiation environment they're flying through.
A very visceral reminder. Okay, this brings us to the big question hovering over all this discussion about instability and weakening fields. Is this SAA the beginning of the end? Is it a sign that the Earth's magnetic field is about to flip?
Ah, the geomagnetic reversal question. It's a huge topic, and honestly, the data and the experts are a bit divided, or at least the interpretation is complex. There are points for seeing this as a precursor.
Okay, what's the argument for an impending flip?
Well, first, the main field, the dipole part, think of it as the big bar magnet component, is weakening faster than the long-term average. Its current decay rate is actually comparable to rates seen in the geological record during past reversals or near reversals.
So the main shield is dropping unusually fast.
Yes. And second, statistically speaking, we're kind of overdue. The last full reversal was about 780,000 years ago. The average time between reversals looking back millions of years is maybe closer to 400,000 years. So it's been a long time.
Overdue based on the clock. What else?
Third, while the main dipole field is weakening, the energy in the non-dipole parts of the field, the more complex multipole stuff that relates to anomalies like the SAA, that energy is increasing quite sharply. It suggests the dynamo in the core is becoming more, well, chaotic or multipolar.
Okay, faster decay, overdue timing, increasing complexity. That sounds like a pretty strong case for something's about to happen. What's the counterargument? Why wouldn't this be the start of a flip?
The main counterargument comes from looking deeper into the past, using paleomagnetism, studying rocks and sediments that recorded the ancient magnetic field.
What do the old rocks tell us?
They tell us that when the field actually flipped or even had a major wobble called an excursion, the overall strength of the main dipole field, what we call the dipole moment or DM, dropped dramatically.
Like really plummeted.
Yes. Think of the DM as the master strength meter for the Earth's magnet. To get a major event like the Lachamp excursion about 41,000 years ago, the DM fell to less than half of what it is today. For the last full reversal, 780,000 years ago, it likely dropped to less than 1/10 of its current strength.
Okay, so how strong is it now compared to those thresholds?
That's the key point. While it is decaying, the current dipole moment is still relatively high compared to those known reversal or excursion thresholds. We're just not seeing that kind of catastrophic drop in the fundamental field strength yet.
So the SAA is a big regional weak spot, but the main global field, while declining, hasn't collapsed to crisis levels seen in the past.
Exactly. And furthermore, the paleomagnetic record also shows that there were times in the past, like between 30,000 and 50,000 years ago, where there were similar weak field anomalies, possibly like the SAA, but the field strength eventually recovered and no reversal happened.
So these kinds of dramatic weak spots might just be normal behavior for a dynamic system. They don't always lead to a flip.
That seems to be the thinking. The system is incredibly dynamic. The SAA's growth is genuinely remarkable and concerning for technology, but based purely on the historical evidence of what defines a true reversal precursor, most researchers conclude the SAA alone isn't a sign that a flip is imminent.
Okay, so the consensus is dramatic changes, yes. Immediate pole reversal tomorrow. Probably not, based on the deep history.
The decay might continue for centuries, making the SAA and related issues worse for satellites, but a full flip seems unlikely to be just around the corner based on current field strength.
Right, that wraps up our deep dive then. We've gone from a continental-sized dent in our magnetic shield, traced it back to swirling iron 3,000 kilometers down, and seen how it forces multi-billion-dollar telescopes like Hubble to literally stop working.
It really highlights how crucial these continuous monitoring missions like SWARM are. They give us this unprecedented window into a complex planetary process that's constantly evolving, even if we can't see directly into the core itself.
So here's a final thought for you. Remember that dynamo churning deep beneath your feet. Its fluctuations are directly impacting how we design, build, and operate every single satellite. And since the field changes enough to require updates to global navigation models roughly every 5 years, think about how often the fundamental map your phone or GPS relies on is being subtly rewritten by those deep Earth forces.
It's a powerful connection, isn't it? What happens deep inside the planet directly shapes our technological environment way out in space, and even affects the navigation tools we use every day, a constant reminder of our dynamic Earth.